Stress-strain diagram. So here are our learning outcomes. Learn how stress and strain are related and identify a stress-strain diagram for a specific material, and understand key properties of stress-strain diagrams for common engineering materials. But before we move to the diagram itself, let's first define stress and strain and understand how they are calculated. Stress is a measure of the internal resistance of a material to deformation when subjected to an external force. It's calculated by dividing the applied load by the original cross-sectional area of the material. Strain, on the other hand, is a measure of how much a material deforms under stress. It is calculated by dividing the deformation by the original gauge length of the material. The formula for strain is as given. Unlike stress, strain is a dimensionless quantity. Now let's talk about how to create the stress-strain diagram. We plot stress on the y-axis and strain on the x-axis. By using the formulas we just discussed, you can convert the data from an experiment into these two values and plot them as points on the graph. The curve that formed is known as the stress-strain curve or the stress-strain diagram. The diagram provides valuable insight into how a material behaves under different loading conditions, such as when it starts to stretch, when it yields, and when it ultimately breaks. So now let's look into different types of stress-strain curves. So the first one is the mild steel, which describes a structural steel which is ductile. Before analyzing the graph, let's make it clear that sigma y is the yield stress, sigma u is the ultimate or maximum stress, and sigma f is the fracture stress, which is less than the sigma u. So looking at the graph, we can make the following observation. So the first region is the elastic region, which is linear. So sigma is proportional to the strain. So strain is recoverable, so there's no permanent deformation. Section 2 is the yielding range. So this is the large deformations of strain with little or no increase in load, which is stress. So points at which plastic range starts. So it talks about permanent deformations. Section 3 is the strain hardening. So there's nonlinear increase in stress as strain increases. Lastly, region number 4 describes necking, which is stress decreases as strain increases. This is due to the fact of reduction in cross-sectional area at a localized region. So the next material is aluminum. In the graph, we can observe that this is sectioned off into 3 regions. So region 1 is initially linear elastic. Region 3 describes the no-yield plateau. So sigma y is equal to the yield stress, and the offset method with a 0.2% offset for determination of yield point. And the fourth region talks about necking, which occurs between sigma u and sigma f, which is the ultimate or maximum stress and the fracture stress. Now let's look at the graph that describes the cast iron. So the following graph describes a linear elastic trend. There's no yield plateau, there's no necking, and the ultimate or maximum stress is equal to the fracture stress. Lastly, let's look at the compressive stress-strain curve, which occurs in concrete. Looking at the graph, we can see that Fc is equal to the maximum compression stress. This graph has a non-linear trend, and it's assumed to be linear up to 0.6 times Fc. There's no yielding, and there's no necking. So this material is very brittle, so it has minimum warning before it breaks, and it'll just break. Lastly, let's get through some key definitions. So first, ductile materials. So ductile materials can sustain large plastic strains before it ruptures, so strain beyond yielding. And brittle materials exhibits little to no yielding before failure. So this knowledge is fundamental to understanding how materials perform and is key in structural design, material science, and engineering. In summary, stress is the applied load divided by the original cross-sectional area of the material. Strain is the deformation divided by the original length of the material. And by converting experimental data into stress and strain, we can plot a stress-strain diagram that helps us understand the behavior of materials under loads.